Hey guys, hopefully this video finds you well. This is my chapter 2 video on resonance. So resonance structures, what makes a major contributor, minor contributor, how to deal with formal charges in resonance. This video encapsulates everything on resonance, so hopefully you find this video helpful, and let's get started. So first thing I have here is just kind of the general information about resonance. So resonance is the blending of several different molecules into one. So this doesn't mean that one molecule is different from the other. They are all the same, but different. So one example I have here is a picture of a peach and a plum. A nectarine has features of both. So there is a peach and a plum picture, and a nectarine is like the kind of the formation of both of them into one. So resonance is shown with brackets, and a two-headed arrow. So I put the peach and the plum in here with the brackets that encapsulates both of the resonance structures, or imaginary resonance structures in this case, and the two-headed arrow in between them. All right. Moving on, for resonance, there's two commandments. You could say that you can never break when doing resonance. You should not break a bond, and you should not exceed an octet. So the first one, not breaking a bond, you shouldn't break one of your structures. So the example I have here, we have 1, 2, 3, 4, 5 carbons, and this second resonance structure shows that we take this bond and break it into two separate structures. That should not occur for resonance. You should have the same kind of structural setting in your structures between all resonance structures. Second one here is you shouldn't exceed an octet. So the elements C, N, O, F have only 4 orbitals in their valence shell. They can't have 5 or 6 orbitals. So these are the two kind of overarching rules. And obviously with resonance, there's arrows to show how these electrons move between these atoms. These are examples of bad arrows, stuff that would not happen in resonance. Are these bad arrows. And you can notice with an arrow, let me pick a different color, we have the tail of the arrow, and we have the head of the arrow. The tail, you can see another example right here. The tail is where the electrons are currently, and the head is where you're trying to place them. So these arrows that you have are very important, and you want to be specific on where you put them in resonance. All right. Some common patterns in resonance that will show up. You can choose to memorize these, or if you do enough resonance problems, these will come naturally. But there's some 5 common patterns that occur in resonance. Number 1, if you have a lone pair next to a pi bond, that's a common pattern to suggest that you're doing resonance there. Another one is a lone pair next to a carbon plus. So if a carbon has a plus formal charge, +1 formal charge, that's another indication, as well as a pi bond next to a C plus. If you have a pi bond between one electronegative atom, that En stands for electronegative. So let's say you have a pi bond between a carbon and an oxygen, like so. You can do resonance by putting that pi bond up into the more electronegative atom, that oxygen, and you can have a resonance structure that looks something like this. Okay. Last one here is the pi bonds around a ring, which are really simple. If you have, let's say, a benzene where you have 3 pi bonds, you have 1, 2, 3 pi bonds, what you can do is resonate around that ring. And you'll end up with, this is kind of going to be a sideways resonance formation, that your new pi bonds kind of look the same, but kind of look different. They showed up here. If you resonate around the ring, it'll look the same but in different places. Okay, so those are the 5 common patterns for resonance. Let's get into major and minor contributors. Okay, there's kind of 3 rules and what makes a major contributor versus a minor contributor. There's 3 very big rules. The first one is that the major contributor has most of the filled octets. So in the example here, this would be the major contributor because our oxygen right here, or I'm sorry, that's the carbon. Our oxygen right here has an exceeding octet, but it's still filled, right? It's filled, but it has 1 more than it wants. That's why it has a +1 formal charge. And our carbon has a filled octet. It has 4 bonds, so it doesn't have a formal charge. In this minor contributor, the carbon right there does not have a filled octet. So a major contributor has all their filled octets. Second rule is that you want the resonance structure that has fewer formal charges. So for the example I have right here, we have one that has 0 formal charge, and this one has, it looks like it has a plus and a minus, so let's say that's 2 formal charge. So if you have these kind of structures, you want to choose the one that's major that has the fewest formal charges. And there's some examples that are great for this, so we'll get into that in this video. Third rule here is that let's say you have the same amount of formal charge. So in these 2 examples, we both have a -1 formal charge and a -1 formal charge. So our formal charge is equal. The octets are the same, right? We have that's designated by the formal charge as well, but we have this oxygen that doesn't have a filled octet, and we have this carbon that doesn't have a filled octet, so that's the same. So let's go to our third rule, which is if you have a negative charge on a more electronegative atom, that resonance structure, that resonance contributor is major. So in this example, we're dealing with a negative charge on oxygen and a negative charge on carbon. Since oxygen is more electronegative than carbon is, this first structure, let's call this the first, is our major contributor. All right, so those are the 3 rules. And again, if you do enough practice problems with resonance, it becomes like clockwork, honestly. So yeah. Next rule here, which depending on what section or class or course you're in, you'll get into delocalized and localized lone pairs. It's pretty simple. Delocalized means that the lone pair can contribute in resonance, and vice versa. Localized means that I would say the word landlocked. It's locked in at its position. It can't resonate within the structure. So the example I have here, this first one is localized because you can't really put this lone pair into any contributing resonance structure, so that doesn't really count. But this one is delocalized, right? And what would that resonance structure look like? I put this question here because I want you to think about what the resonance structure is, because if it's delocalized, it means it can at least resonate once. And what would that resonance structure look like? Let's draw an arrow, because we know these pi bonds have to go somewhere. Let's put these pi bonds on this bond, which means that this carbon would exceed its octet, and we don't want that. So we have to put this double bond somewhere. Let's put that double bond at the end. And what would this structure look like? Something like that. Now I know what you're thinking. Sam, didn't you just say in one of your rules that you cannot exceed an octet? We're technically keeping the formal charge, right? Our formal charge at the start of this was 0. We didn't have any formal charge, and we have a +1 formal charge and a -1 formal charge. That still equals 0. So our formal charge stays the same, which is why we can do this. And that would be the resonance structure for this. This is why it's a delocalized lone pair, because that lone pair can resonate out of that nitrogen. Okay. Hopefully that makes sense. Let's go through some examples. I believe I have 3 or 4 different examples for this. This first example just asks for the resonance structures for all of these molecules. So I'll rewrite this first one. Remember, you can fill in your lone pairs as well. So this nitrogen will have 1 lone pair, that oxygen has 2 lone pairs. Our only formal charge is on this carbon right here, all right? So let's move that +1 formal charge around. We have lone pairs right here that are delocalized. Let's put them in right here, and let's see if we can do that resonance structure. We end up with a double bond right there. This carbon now has 4 bonds, so it doesn't have a formal charge anymore. But this nitrogen also has 4 bonds, and it only wants 3. So that receives a +1 formal charge, and our formal charge stays the same. You should see within all these resonance structures that you should have, for this first example, all of them should have a +1 formal charge for each one. So you should have a plus somewhere in your resonance structure. All right, and let's get this oxygen involved. That's another resonance structure that I see could happen. And again, this is all going back to these common patterns that we see. So we have a lone pair next to a pi bond. This one that I just did was a pi bond next to a more electronegative atom. So you can see we have a pi bond, that's our double bond, and the oxygen is your electronegative atom. We're shifting that pi bond towards the electronegative atom. So our resonance structure should now look something like this. The nitrogen has 3 bonds again, so it doesn't have a plus charge on the nitrogen. That plus charge goes to that oxygen. All right. And I know these brackets, let me make some more space here to understand these brackets if I can. Maybe not, but in your paper you should have probably a more concise bracket thing where it should go all in one line, not going down like this as well. But that's okay too. Now let's go to this aromatic compound here. We have a C plus, so we know that's one of our common patterns. So this can do resonance. Let me just rewrite this compound. We have 3 pi bonds and then a methyl group coming out. All right. So going back to your common patterns, I'm not going to skip back to it, but always feel free to go back to those. We can actually take this pi bond and place it over here, right? So our next resonance structure should look something like this. All our 2 pi bonds stay in the exact same place. And now which carbon should have that plus? Because we know all of our resonance structures should have a +1 charge, so that +1 has to go somewhere. I would say it ends up right here, right? Because this originally has 4 bonds connected to it. And if you go to its next resonance structure, it has 4 bonds still. But this one started out with 4 bonds, no hydrogens. And now it has, it has 3 bonds and 1 hydrogen. And now it has 2 bonds and 1 hydrogen. So now it has only 3 bonds. That means there's a plus connected to it. All right. We can move this pi bond to create our next resonance structure. Everything else stays the same. Now that plus charge will go right there. Now let's seek out this other pi bond to make another resonance structure. You can see it goes all around this aromatic ring here. So then our plus charge is right there. And then finally, to end it off, we can put this pi bond that we originally put in our second resonance structure, we can finally put back in its place. So this is kind of going to go down here. And now we have 3 bonds in there again, and we're left with a similar structure to our first structure, except the pi bonds are in a different order around the ring. So we have 1, 2, 3, 4, 5 different structures right here. Okay. And again, this one we're not focused on major and minor. It's just getting down all the resonance structures. This last one's pretty straightforward. There's only so many you can do with this compound because you don't have any pi bonds, right? You don't have any double bonds in this compound. So let me rewrite this. We have a plus carbon. I'm going to fill in the lone pairs there. We have this nitrogen, which has a lone pair. This lone pair is going to drop down into this bond to create a full octet for that carbon, which leads to this structure with a plus charge on the nitrogen. And that's the only resonance structure you can make for this one. Okay. Hopefully this is making sense. I know I'm kind of all over the place with these drawings, but it can get messy. And when you're in an exam or you're just doing practice problems, remember that you can always erase your problems, think of them again, think about all the possibilities. So yeah, let's go to our next practice problem. This next practice problem says draw all significant resonance structures for the following compound. So this one does have some double bonds, so we'll get some more structures out of this one. Let me rewrite this. And remember, when you're doing resonance structures, the question in the example is a resonance structure. So you add that in your bracket. You don't move bonds and then that's your first resonance structure. This is your first resonance structure. So you can label that 1 if that helps. Okay. So same thing we did for the last example. We have a lone pair connected to that nitrogen. We can add it to the bond. So let me show what that would be if I just ended off with that. We would have a nitrogen with 4 bonds, so it would have a plus charge, but we don't want a plus charge, right? Now we have this carbon that has a filled octet, which we don't want. This has 5 bonds, which it shouldn't. So we need to do something else in this step. We need to move this bond right there. So you should have a 0 net for your formal charge. And this structure gives you a 0 net, right? We have a plus and a minus that is 0. It's neutral, just like our first structure. So that would be the first resonance structure that would form here. And now you have another double bond that can resonate here. So if we drop this to the bottom to help out this carbon that only has, let's see, 2 bonds and 1 hydrogen, so it needs another bond. Now you would get a third contributing resonance structure. I don't have a lot of space right there. Let's go down. That pi bond would go down there. You still have a plus charge on your nitrogen, but now that negative charge goes to this carbon. This carbon used to have 1 hydrogen and 3 bonds. Now it has 2 bonds and it still has that hydrogen. So you need a negative charge there because it's still missing a bond, okay? And that's all the resonance structures for that one. Remember your brackets at the end as well. All these arrows are good, right? Our tail is showing where the electrons are currently, and the tip, the arrow head here, is showing where they should end up. All right. Oops. All right, last problem here. This question asks to draw all the resonance structures for this problem. So let me rewrite the initial structure here, and let's think about what specific resonance structure is easy to think about here. Well, we have a carbon in a pi bond with an oxygen. That is one of our common patterns off the bat. Oxygen is more electronegative than carbon, so that pi bond can resonate up, and we get our first resonance structure here. I'll fill in all the lone pairs. And this carbon should have a plus charge. Okay. Let's fill in the rest of these lone pairs on this oxygen as well, because it'll make a little bit more sense. There's one more you could do with this one. And remember, you want a resonance structure that has a plus and a minus, because the original one had a neutral formal charge. This one has a plus and a minus, so your third one should also have a plus and a minus, or it should be neutral. Okay, so let's think about this last one. You have a C plus right here, so you have a C plus, and it's right by a pi bond. So you have lone pairs right by a C plus. You can drop those lone pairs to make that carbon have its 4 bonds. So your final resonance structure, this would stay the same. But now that plus charge would go at this oxygen, and that oxygen has 3 bonds now. It only likes to have 2. So if it has 1 more than it should, that's a plus charge. All right, and remember, finish off your bracket here. So that's resonance. You'll get the hang of it if you do enough structures. Obviously, there's more complex structures. Next video, it'll probably be uploaded. I have additional practice problems on resonance. I have about 7 different problems. So definitely feel free to check out the next video as well. Thank you guys for watching. I will see you guys in the next one.